So in the last video we talked about matrix inverse. In this video we're going to quickly go over matrix transpose. The matrix transpose is actually a pretty cool and fairly unique operation to matrices, as far as I understand. So it'll come up in the first machine learning model we're going to be going over, which is why I'm going over it now. So when we write the transpose, so let's say we have some matrix A, then transpose of A we write that as A T. So that's just a simple notation. It's an A with a T on top. I'm going to write that really big just in case it doesn't come out too well. So A with a big little T on top, usually a capital, or always a capital T. So how does the transpose operation work? So first I'm going to just go through an example. So let's say A equals, actually I might be going too far over to the side, 1 second. So say A is equal to 1, 2, 3, 4. So what you can think about here with the transpose is that you kind of draw some kind of line along this axis and then flip the matrix along that axis. So that means that A transpose is equal to, so the diagonal stays in place, the diagonal doesn't move. So it's going to be equal to 1, 3, 2, 4. So notice that the 2 and the 3 switch places there. Let's just do another example where it's not. So this is obviously from the last video. This is 2 by 2, which is square. Ooh. So let's see what happens when A is not square. So let's say that A, actually let's just do B. Why not? Let's change it up. Let's do B. Just B is equal to 1, 2, 3, 4, 5, 6. So I'm going to do another similar thing. We're going to draw a diagonal like that. And we're going to flip it. So that means that B transpose is equal to, so 1, 4, shoot. I don't have an eraser, okay. So you're going to notice that this is going to go from a matrix that has more columns than rows to a matrix that has more rows than columns. So then 1, 4, 2, 5, 3, 6. Another way that I like to think about it is you essentially just like take this and rotate it 90 degrees. Actually, I guess, no, it's not like that because that would, the elements there would be switched. So it's something that you kind of just have to do a couple times to get an understanding. These ones are a lot trickier than these ones because you have this weird rotation of like changing of orientation essentially. So in the general case, so B is M by N implies that B transpose is N by M. So we're essentially just switching the rows and columns. So you'll see here that I go, okay, this is the first column, now it's going to be the first row. This is the second column, now it's going to be the second row. This is the third column, now it's going to be the third row. So we can just like group these all together. Those become those. That's another way to think about it. So one thing to note that's important about the relationship between the transpose and multiplication is that, so first of all, A, B is not equal to A, B transpose. That should be pretty obvious because the dimensions are switching, so you're going to get some kind of different interaction. And odds are that B transpose might not even be compatible with A because of the dimensions getting flipped. But one thing that is true is that let's say you have A, B transpose. So what's that equal to? So that's actually going to be equal to B transpose A transpose. So this is an important property that we may or may not be using in our next derivation. We'll have to see. But this is something in my machine learning class, we use this property quite often. So then that means, like, let's just give an arbitrary example. So if we have C transpose D, and then we want to take the transpose of that, what's that going to be equal to? That's going to be equal to D transpose C. So in general, the transpose is kind of a weird operation, but I think it's still important to go over. In your linear algebra class, when you eventually take that, which I'm assuming you will, you'll see a lot more about how important it actually is. But for our purposes, I just wanted to quickly go over how does it work. Like, you're going to see an AT in some of our derivations, and you'll be like, what the heck does that mean? So I just kind of wanted to quickly go over it. Also, this right here is key. Just draw an exclamation point. See, teachers do that sometimes. So that's key. This is key. And then just understanding this whole flipping the rows and columns is also important. One last thing I wanted to go over is that, so with our vectors, so if we had some vector 1, 2, let's call it B. We had another vector U, which is just equal to, just make equal to 1, 2 as well. Then what you'll notice is that if we treat these as matrices, so if we treat, so V is, what would it be? 2 times 0, and U is 2 times 0. Well, notice this implies that VU, under the matrix multiplication we just talked about, does not exist. Wow, I forgot the N. D little n-e. So what we actually do to write the dot product is, you notice that V dot U is actually equal to VU transpose. Let's actually change these numbers real quick. And so you see V dot U is just 1 times 3 plus 2 times 4, and then VU transpose, I wrote squared, transpose is going to be equal to 1, 2, 3, 4. Sorry, I'm probably crouching in front of it. So using the matrix, wait, I think I messed this up. Okay, transpose is actually supposed to be on the V. So transpose is on the V. So we have 1, 2, 3, 4, which is again just going to be equal to 1 times 3 plus 2 times 4. So that's just a quick thing to note. So anyway, hopefully that gives you some idea of how the transpose works. From here, I'm probably going to be going into, hopefully I'll be going into a model. I think I'm going to see how people feel about this. I think I'll probably go into a linear, like the general case of a linear model, a linear machine learning model next, and kind of build off the previous machine learning video. So anyway, hopefully this was useful. Hopefully this quick series of matrix algebra and linear algebra is useful. Again, you're going to get way more, and you're going to learn quite a bit more about the significance of all these operations in your linear algebra class, but we have a lot of freshmen in here who haven't taken a linear algebra class and probably won't for another 2 or 3 semesters. So just quickly going over this to make sure we're all roughly on the same page.